In this video, I wanted to explain how do we find minimum and maximum spanning trees. And basically, there is what we call Kruskal's algorithm for doing it. And I want to get to that in a second. But before we do, let's just kind of talk about the basic concept and talk about solving a problem without really much other information. So let's look at one example similar to the very first one we looked at in the introduction video. It says, consider the following network with weighted edges, where each of the edges represents the cost in millions to build power lines connecting each of the following cities. Find the spanning tree of minimal cost and maximal cost, and find those total costs. So basically, we can see that here we have 5 vertices, and so we're going to need 4 edges to make a minimum spanning tree. And we want to imagine that each of these are towns currently without power, and we're trying to build these power lines to route power between each of the cities. And our sub goal here is to find that spanning tree, but find which one costs the least amount of money. And basically, we can see that each of the numbers would represent the cost to construct each power line in millions of dollars or whatever. So basically, if we're thinking about, well, how would we solve it? But of course, if we're trying to find the cheapest configuration, we want to use the smallest numbers. So it's pretty obvious where we begin. And you could imagine, well, we could start by building the power line between E and C, which would cost $1 million, right? And that would give us one option. I could build the power line between E and D, which would cost $2 million. And I could keep doing this until I use 4 edges, right? Because I know that my number of vertices is 5, and the number of edges that I need would have to be 4 in order to connect them all together. So then I could use the next cheapest edge, which is $3 million between B and C. And each time I can imagine building these power lines, I can imagine that now these towns have power. D, E, C, and B have all been linked together. And you might be wondering, as a separate question, well, where is the hub of the power, right? Where is the power actually coming from? But that's never necessarily something that is, it doesn't really matter as long as one of the towns have power. Once they're all linked together in a network, the power will flow through them all. But notice there is an issue that we run into when we're connecting together each of the cheapest edges, right? If we look at well, what's the next cheapest edge between B and E is $4 million. But if you think about, well, should we use this edge when we're building our network, when we're trying to find a spanning tree? Well, the obvious answer is no, because notice that if we were to construct that edge, it would make a circuit right here, which basically, if we're thinking about this B, C, and E, they already all have power. Building this power line would do nothing because, well, not necessarily nothing, but it would not add anywhere new to the network. And that circuit is a property of, well, a tree is not allowed to have circuits. So this edge would not be a part of the spanning tree, and it would be invalidated as we're progressing in this problem. So when you're actually selecting the edges for your spanning tree, there's certain edges you got to skip, and that's really what you want to look for. And then the last edge, or the next cheapest edge, would be between A and B, which is 5 million, and that would finish our spanning tree using 4 edges completely, and that would be the minimal way of connecting these 4 cities together with power. And if we add up all of those costs, 1 plus 2 million plus 3 million plus 5 million, that's a total of $11 million, and that would be our final answer here. What's the cheapest way to build power lines between these cities. And actually, one other thing I wanted to just mention as we're on the topic is sometimes a minimum spanning tree is not the best answer, because one of the things you might be thinking about if we're actually going to construct all these power lines is, well, what happens if one of them is debilitated? Or let's say, there's a storm and a tree falls on this power line after I've constructed it, and later on in the future. One of the issues with a spanning tree, minimum spanning tree, is that while everything is connected, if one of the connections goes out, it isolates part of the network and part of it gets completely disconfigured, which is a huge problem, right? Because in the real world, a lot of times we do have problems where we sometimes would want to have a backup. So I wanted to, explain, well, while a minimum spanning tree is an important idea and an important concept for connecting things in an efficient way, sometimes we want to have a secondary connection or a backup, like say, for example, we might actually build this power line 4 as well, just so that we have a backup. And that's a lot of money. And so it would be something where if we actually work for the power company and we're actually in charge of this construction, it's another aspect of this problem. But I think you can see, a lot of times we're kind of ignoring those things for the sake of completionism, solving a perfect problem. But you can imagine, I just wanted you to think about sometimes minimum spanning trees do have issues, and while they are the best solution, right, it's not necessarily the end of the story for a real problem. And also, let's do one more example. I'm finding a maximum spanning tree. It would be pretty much the exact same procedure. Let's say that these numbers, instead of representing how much money it costs to build the power lines, let's say that this is how much money we're going to be getting for building the power lines, right? Say we're the power company and we want to make as much money as possible. Um, and we want to know, well, which configuration would get us the most money, just as a, alternate construction. Well, in that case, we'd want to build the most expensive power line so that we could make the most money. And we'd want to find what we call a maximum spanning tree instead of a minimum spanning tree. And basically, if I were to do the same procedure where I'm connecting the dots using the biggest numbers, I start with 12, 7, 6. Again, in the same way, I want to make sure that every edge I'm adding is bringing something new into the network, and I'm still using n-1 edges. Actually, notice if I just use the 4 most expensive edges here, there are no circuits, and this is a spanning tree without really any second thought. I don't have to skip anything as I did in the example to the left. And my maximum spanning tree here would just be consisting of 12 plus 7 plus 6 plus 5 for its total net weight, which is 30, I believe, doing that in my head. And so basically we could make $30 million if we were if that was a separate problem. But my goal here is to illustrate what is a minimum and maximum spanning tree. How do we actually find it? And to wrap up this video, I wanted to talk about Kruskal's algorithm. In the next video, we'll do a few more examples of solving minimum and maximum spanning trees from scratch using this algorithm. But now it should make sense why this works based on the above example. So Kruskal's algorithm is an algorithm for finding the minimum or maximum spanning tree. Well, technically it's minimum spanning tree, but it's easily adjusted to find a maximum spanning tree. It says to do step 1, pick the cheapest edge available. And it says in the case of a tie, pick one at random. So it shouldn't typically matter. If they're the same weight, you could pick either one. Sometimes you might need both. But if there is a tie and you can only use one, it says pick randomly. It does not matter. Step 2, pick the next cheapest edge and mark it. And so basically it's exactly what we did, right? We're going to highlight the cheapest link. And actually, another thing I wanted to mention about this algorithm is it's actually almost exactly the same algorithm as the cheapest link algorithm from chapter 6 that we just did in last chapter, with one notable difference, and that's the last step. It says step 3 for all the way up to step n-1. Continue picking and marking the cheapest unmarked edge available that does not create a circuit. So there's one important thing that you have to pay attention to when you're using Kruskal's algorithm. Basically, pick the cheapest edge, pick the next cheapest edge, so on and so on and so on. Just basically you're never allowed to make a circuit, because when you're forming a spanning tree, circuits are not allowed because it's a tree. So in order to keep a tree, we're always picking all the cheapest edges but never allowing a circuit. And actually what's very nice about this algorithm is guaranteed to give you the best solution there is, unlike the cheapest link algorithm. So with Hamilton's circuits from chapter 6, those are a little bit harder because we're actually forming circuits. And these systematic procedures, these algorithms don't necessarily give you the best answer. They typically give you a very good answer, as we talked about in all of chapter 6. But what's nice about this chapter is there's only one algorithm, and this will give you the right answer. So it's a lot simpler to formulate spanning trees, and we don't have that same issue with actually closing our circuits. And this is totally different than Hamilton circuits and paths, because we're not actually walking around or traveling between these points. We are allowed to use more than 2 highlighted edges. And that's the one difference between this algorithm and the cheapest link algorithm, is in that algorithm there were 2 conditions, right? We were not allowed to make a circuit, or never close a partial circuit as I phrased it before. And the second rule we were not allowed to do was we were not allowed to have more than two highlighted edges between a point. But notice that in spanning trees, we are allowed to have more than two highlighted edges going into a point because we're not trying to formulate a path where we're going in and out and in and out back and forth between different points. We're just trying to build power lines or railroad networks or roads where it is perfectly fine to have more than two things, power lines stemming from one point. And that's really the only difference. And also, we're not closing our answer. We're not finishing the circuit at the end as we did in chapter 6. We are never making any circuits at all.